What's up, mga ka-ChE? It's Gradle here, and we are continuing where we left off. This is the part 3 on the evaporation at practice test in the MRII book. So please bear with me. So as we finally solve the last 5 problems left in the book. Okay, so let's begin. We left off with number 21. Number 21. So this is really I remember we had this as a quiz, or maybe even a midterm exam, I think, back in my heat and mass transfer subject, and we really did not answer this. Or maybe the most intelligent in our room answered this, but I for one did not answer this problem. Okay, so let's move on. So this problem so if you can see, this is a really weird problem, and also the solution is very weird. So this problem came from Coulson. Okay, so this problem came from Coulson. Please find it there. Okay, yeah, you can find it there actually. So uh, number 21, number 21. So have to draw our diagram. So we have two effect evaporator. So we have V1 and V2. Okay, so we have that. Now let's go for the overall material balance, diba? So overall material balance, so you can see we have two streams na of V, diba? So we have V1 plus V2. Then the only one that got out is L2. Okay, so we have CMB also. And if you think um, this solution is weird, just ask also why solution is weird. So you have FXF L2 is L2, ba? And then so you have L2, you have 2.5 times 0.15 over 0.55. So you'll get 0.62 kilogram per second. Okay, so you now get the overall temperature overall temperature difference. Okay, we have 126, di ba? 126, which is 399 temperature of the steam, so 399. And also you have 57.8, okay, minus then 6 BPR. You have 62 1.33 Kelvin or degrees Celsius. They are the same because it's delta T man po. It doesn't matter. Yeah. So we have to get our T1. The T1 is equal to 62.33, 1.1.8, 1.8 plus 1 over 0.63. Well, you know the drill. So we have 16.16K, but in the in the in Coulson, he rounded this to 17 Kelvin, and also for T2 you will get 46.7K, diba? But he rounded this down to 45. I don't know why. Yeah, so let's draw the profile, temperature profile, temperature profile. Siguro he made this so that the scaling will be easy. So we have 45 here, and then we have 6. This is 126, diba? Temperature of the steam. So you have 109 degrees Celsius. So you have also 64 degrees Celsius here, and then lastly you will have 58 degrees Celsius. Okay, so in Kelvin you have this is 399. Yeah, you have also this is 382, then 137, then 331. So this is from Coulson also. These values are from Coulson. Okay, so just tabulate all the values. Okay, and from in his book, they are all in lambda na siya, nakalambda. So meaning the enthalpy of the liquid was already subtracted from the enthalpy of the vapor. Okay, so that those are these values, and I also check them with the values in Paris. They are near. Okay, they are near from the values of where in Paris. Okay, V2 and S, we have 2.5 kilograms per second here. Don't know this yet. We have 102, 109, we have 58, and then we have 126. Yeah, so we have 2,132, 2363, and then we have 2185. Yeah, so let's move on. So we have to get our heat balances na. Okay, so HB first effect. Okay, so this is weird because diba we are used to FHF plus S ana. What he did was he transposed this to the left side. Okay, so the FHF is now not no longer on the left side but now on the right side. I don't know why. Okay, so V1 lambda V1. Okay, lambda V1. So you have 2185 S plus 2.5 times 3.75. HF is CP delta T. Okay, that's HF. You have a 109, 102 plus V1, 2232. Then okay, so you have This is the temperature of the feed, 102 degrees Celsius is temperature of the feed. Okay, so you have to S minus 2232 V1 is equal to 65.625. So this is equation 1. Take note of that. So at second effect, you have V1 LV1 plus L1 HL1 minus V2 LV2. Okay, but we have no, diba wala tayo L1, okay, L1, but we can improvise. So F is equal to L1 V1. Okay, we can take advantage of that, F minus V1. Okay, so let's substitute 2232 V1 plus 2.5 V1, 2.5 minus V1 times 3.75. So HL1 here, he made it as a CP delta T also. Okay, CP delta T also. So 109.64. 64 is the temperature of the second effect. Okay, ini siya, 64. Ano siya. So at second effect, so manda yun is you have 2363 V2. Okay, so if you transform that to a nicer this is 2.5 ng F this is 2.5 minus V1. Let's substitute here. Okay, 2 minus 2, 3, 6, 3 V2 is equal to negative 421.875. So keep this as your equation 2. Now we are nearly done with this horrible problem, and I can't really wait to have to be done with this already. Yeah, so you have your OMB. So OMB, diba? You have your OMB. F is equal to L2 V2 plus V1. Diba? You can take advantage of that. V1 is equal to F minus L2. Diba? So we know L2 and V1.682. So we have V2 plus V1 is equal to 1.818. So this is your equation 3. Put it in your calculator, solve simultaneously. You can get cursor. So S is equal to 0.923 kilograms per second. Then you have your V1 is equal to 0.875 kilograms per second hapon, and V2 is equal to 0.943 kilograms per second. So V1, we were asked for V1. Just multiply this by 60 and you can get 32.5 kilograms per minute. Yeah. So this number, letter B, number 51. Okay. So now we will have to solve for 22 and 23. Diba? The heat transfer area at 1 and heat transfer area 2. Okay. So it's actually easy. So let me delete finish siya the slide. Okay, so we can make room for another. So we have 22. You have A1, you have your area 1 is always the steam. Okay, so yeah, it's 0.924 times 2185 over 1.8 then 17. Yeah, you have 66 square meters. Okay, so for number 23, you have A2 is B LV lambda V1. Okay, so you have U2. Okay, yan. So you have 0.875 times 2232 over 0.63 times 45. Okay, you have 68.9 square meters. So this is letter B, letter B, and then letter C. So okay, so last two problems. Okay, last two problems. So number 24. So what is the case for number 24? Okay, so we have and we have this tube. Okay, this tube. It is being heated. Okay, so it's being heated in a tube. So you have 284,000 BTU per hour now. So you have V and also L. Okay, one man down. Because this is being heated, so part of the water that goes passes through this tube gets evaporated. Okay, so how do we account for the fraction that was evaporated, diba? So this is all. Let me list or draw the given first so that I will have a picture of what is going on here. Okay. So this is what I have got from the steam table. Okay, please check them out. It is at 130 degrees Fahrenheit. Siyempre, you have to convert that to Kelvin. So please do so. So this is what you will get. 97.676 BTU per LB, and then you have the density at 130 degrees Fahrenheit hapon is 61.54 BTU per LB. Oh no, per LB. LBM per cubic feet. Okay. So at outlet, kini, diba? You have 4 psia, or this is 27,579.2 pascals, diba? Or you can get the saturation temperature at 340.27 K or 153.1 degrees Fahrenheit. You can get the HB here. HB, diba? The enthalpy of the vapor, which is 1,126.638 BTU per LBM hapon. HL is equal to 120.782 BTU per LBM. Yeah, so we have to find the mass flow rate. Okay, so we are given the velocity, so we can get the mass flow rate, and we have the density, so it works in our favor. Well, we know this tube has an outer diameter of 2 inches and has an inner diameter of 1.87 inches. Yeah, so you have to find out where I get those. Okay, so 1.5 feet per second. Also, this is the density, and then you have to find the area. Okay, this is the area. Then 1.87. This is the inner diameter converted to feet. And you get 1.76 lb pounds per second. So now have to go. We'll now go to the heart, which is the energy balance. So you have your FHF plus the Q, ba? Ayun, the leaving BHB plus LHL. Okay, substitute everything, but we don't the L, diba? Don't know the L, but from the OMB we know that F L is equal to F minus B. So substitute, diba? Substitute and then find for V, diba? Substitute everything. You have this, diba? You have that. Substitute everything. You will get V is equal to 0.080 pounds per second. And then the fraction evaporated, B over F, right? So 0.038 over 1.76 is equal to 0.216. Okay, that's number 24, letter A. Yeah. So number 25, it's relatively easy. Relatively easy. Relatively easy, I don't think so. So number 25, so you have a condenser now. So condenser, which is a spray there, spray. So you have a water there, and then you have water here. So this you have a steam, is 500 pounds per hour being cooled, and then you have your cooling water, spring water at 80 degrees Fahrenheit, and then the condensed and plus the steam, condensed steam and plus the water leaves at 200 degrees Fahrenheit. Okay, so let's list from the steam. We have the steam 25 psia now. So find the equivalent 172 370 pascals. So you have a TS, which is 240 degrees Fahrenheit, and then you have your HS 1160.4. So don't be confused, I got these values from the Paris and transformed them to BTU per LBM. Okay, using the conversion factor I provided for you in the last video. Okay, so you have now your heat balance. Okay, heat balance, you have SHS plus CP delta T. So this is the down SCP delta T. So this is the heat balance that now I got this. I don't know where I got this. Maybe from a cave. I have to check. But I got this from if you have to make an energy and mass balance spray yani set up. Okay, so you have 500 plus 1160.294 plus W. CP is 1, diba? And then 80 minus 32. 32 is the reference temperature of water in degrees Fahrenheit, which is kung i-kuhanin mo na siya sa Celsius, it is 0. but in the Fahrenheit it's 32. Okay, and then you have W 1, and then you have temperature 32, 200 na siya. Dayon plus 500, 1, and 200 hapon, and 32. Okay, solve for W, you will get 4135 pounds per hour. Okay, that's the answer for number 25. That's letter C. Okay, so that ends the trilogy of evaporation. I hope you have found this uh, helpful. I know I glossed over, I went too fast, but I want you to not rely on me, but on your own understanding. I'm just helping you understand what you have, or affirm what you have solved. Okay, so it's just to check if you have understood it. So yeah, please subscribe if you haven't do so done so, ba? And click the notification bell so that you will get notified in every time I upload my videos. Okay, so that's it for my 3G, and God bless. I hope this has helped you greatly. Okay, bye.